So last class, what we were doing is we tried and established this formula that is of the electric force. We were talking about electric fields, and using Coulomb's law, what we established was there's a force whenever you have any amount of charge existing or in the vicinity of each other. So when having a conversation about 2 point charges, such as Q1 and Q2, um, you get to see that they interact. And when they interact, they apply a force on each other. So let's say I have a positive piece of positive charge over here and a piece of positive charge over here. They're going to interact with each other. That is, both have their own individual fields, right? So they have their own individual electric fields. So these two charges, consider them point charges, with the similar idea that you had in gravitational fields, right? In gravitational fields, what did you study? We consider masses to be point masses because all of that field line seems to come and meet at this one singular point, right? And that point, with respect to that point, we say the mass is a point mass. So we attribute all of the mass properties or gravitational properties to this one point and consider it a point mass for our calculations. Because when we have two masses, we consider the separations as such as this from one center to another. With a similar idea, we also say point charges, okay? Or sometimes you'll see test charges. With respect to charges, the conversation is like, charges itself are very small. So you can really just say it's a charge and it doesn't really matter because we're not talking about large masses. But anyways, you will hear point charges as well. Um, but yeah, so similarly over here, when you have two sorts of, let's say, charges existing, one positive, the other positive as well, notice the field lines are outwards. And this is a property that I will discuss. Why do um, positive charges have outward fields and negative charges have fields that are inwards? So these are field lines of two separate types of charge. So the reason, I'll give you a brief idea why we draw the field lines as such as this. Whenever you're having a conversation of electric fields, that is, what are the electric field lines of a negative charge and how does the electric field lines of a positive charge look? Whenever you talk about field line, you consider in what direction will a force be applied if a test positive charge is introduced. I'll repeat. Whenever you want to find the direction of electric field lines, you consider a test positive charge near the charge and see in what direction will the force be applied. So when I have a test positive charge here near this negative charge, which direction do you think the force is going to be applied? Towards the negative. Yeah.
Away from the positive.
Away from the positive, this positive. So towards the negative, right? It will be an attractive force, right?
Yeah.
Exactly. So they're opposite charges. So the field lines for this negative charge will simply be inwards because what happens when I bring a positive charge, a test positive charge, it's pulled in from all direction, from all direction, from all direction. Got it?
Yes.
Yeah. So similarly, when I have a positive charge over here and I bring in a test positive charge, that is the highlighted one, what happens? There's going to be repulsion because there are similar charges. So when I bring in a test positive charge, the highlighted one, it gets repelled. I put it here, it gets repelled in this direction. I put it here, it gets repelled in this direction. I put it here, it gets repelled in that direction. Point is, for a positive charge, then the field lines will be drawn outwards. So that is why for a negative charge, you draw field lines that are radially inward, and for a positive charge, you draw field lines which are radially outwards. So this is the main idea. I do discuss it later on, but I'm giving you a brief idea of here. So what I was initially saying, the conversation started with having two charges over here, point charges, and when I have two positive charges over here, 5 coulombs, let's say, both, right? What's going to happen? They're going to interact with each other, and there's going to be a repulsive force between them because they're like charges. So they have a certain amount of um, electric potential energy over here. And that EPE, I discuss it later on as well. I'm giving you a brief idea right now. This electric potential energy will be positive. You know why? Because this is a repulsive force over here. So them being like charges are pushing each other. However, there's an external force being applied to the positive charges such that they are unable to move apart. So let's say they are um, 5 meters away from each other, right? Like in a natural scenario, in an isolated infinite system in space, if the positive charges were 5 meters away and you release them, they would go to infinity on either end, right? They would move away from each other till infinity because they're repulsive forces. Okay. But since they are static at 5 meters away from each other, you can say there's an external force being applied to them such that they're sticking at this position that is 5 meters away. Hence, I am working. Yeah.
We're talking about electric potential at a point in an electric field.
Yeah, I'm talking about the electric potential energy of the charges. Would their energy be potential energy be positive or negative? I'm trying to connect the idea with gravitational potential energy over here.
Right.
So in gravitational potential energy, you knew that the energy would be negative in all cases because it was always attractive force. So basically, you said in terms of gravitational potential energy, what was the definition? The amount of energy needed to bring that mass from infinity to a defined point near another mass. So if there was a mass over here and there's a mass over here, what was the energy needed to bring this mass from infinity to here while there is this massive mass? So what was the energy? In this case, it would have been the work done would have been negative. Why? Because it has lost energy, attractive forces. It's feeling a force here, and this mass is feeling a force in that direction. They're attracted to each other. So in this case, the potential energy of this and this, both, if these two are in an isolated system, both will have a GPE that is
Negative.
negative. Exactly. But the contrast that I'm drawing over here is with respect to electric fields, you can have repulsive forces as well, such as positive charge. So in this case, I'm saying in this isolated system, such that there are no other charges, they will have a repulsive force. Hence, the fact that they're just 5 meters away from each other, they're supposed to push each other away and go to infinity. But since they have been forced and brought together at this 5 meters distance, they have some amount of energy within them. And that energy is positive. Why? Because some work has been done on both of these charges to bring them this close together. So they've gained that energy and they have a positive electric potential energy. If they were opposite charges, though, it would be the same case as gravitational fields, uh, such as that is having negative, right? So that's the point. So I'll go more in details about electric potential energy, but I'm just giving you an idea. So what we discussed last class is with respect to Coulomb law, we came across this formula that is force is equals to K times charge 1 times charge 2 divided by separation squared. So this is the ultimate formula that you have. Okay. I also discussed what permittivity is. But yes, so if you have two charges, Q1, Q2. Now, what happens if I have one positive and one negative charge? So let's say this is 5 coulombs and this is negative 5 coulombs. You plug this in and you also plug this in. What will your final answer be, positive or negative?
Negative.
Negative. So this is the beauty of this equation, that you ultimately get the true nature of the force acting. And you'll see this again with electric potential energy. That is, when you have opposite charges over here, it shows you that they are attracted to each other. Okay, so when I go to electric potential energy, electric potential energy, the formula will directly give you if there is like charges or opposite charges. So whenever you plug in the charge itself, the ultimate value that you get will either be positive or negative. And based on the value, you understand that are like charges interacting or unlike charges interacting. Whenever there are positive and positive charge or negative and negative charge, the ultimate answer becomes positive. So your potential energy is given as positive. I'll show you that. I'm just explaining right now. But yeah, point is when you have again opposite charges in that equation, your ultimate answer is given as negative, as such as you saw over here. So the electric potential energy equation is very similar to this, and I'll show you the derivation for it. But yes, this is the force equation, and over here, when you plug in the value, the ultimate answer, whatever it may be, is basically the force on either of the object. So over here, the sign doesn't matter much, if I am being honest with you. So if the ultimate answer is negative, doesn't really matter. The magnitude of force is same on both. So if I define this side as positive, right, as positive, and this as negative, and I say, well, I want to understand what is the amount of force on Q1. Let's say I want to find that out. And this is positive 5, and this is minus 5 Coulomb. You plug in all the values, and your ultimate force answer will be, as you mentioned, negative, right? Now, on the positive charge, since these are attracted to each other, which direction will the force be on the positive charge? What do you think? Left or right?
To the right.
To the right. Perfect. So this is the force, right? This is the direction of force. So technically, the answer that you got was negative, but the direction is in the positive direction. This is why I'm saying in case of the force equation, the sign that you get doesn't really matter. It is not going to matter much. It will matter when you have the potential energy. So over here, when you get the answer, it is positive or negative. It is simply your perception. What are you finding out? Because whatever answer you have over here, even if it's negative, that is not wrong. Why? Because for this negative charge, which direction is the force? Left or right?
Right.
Left, right? So for this negative charge, since it's attractive, on the positive, it is towards the right. On the negative, it is towards the left. So since it's towards left for negative, sorry.
So do that again. To repeat that again.
So I said that what is the direction of force on the positive charge? It will be towards the right. And what is the direction of force on the negative charge? It will be to the left because they're attracted towards each other, right? So the force in case of the negative is towards the left. And
The
what is
direction of the force,
yeah,
not the fluid lines.
yeah. The force, exactly, the force over here. So that is towards the left over here, right? And in that case, this answer that you've gotten is right. It is a negative force value because I've defined left as negative. But in case of positive charge, it is towards the right direction. So does this sign make sense then? Nope. So don't worry about, the reason I'm saying this is whatever value, sign you get in the force equation doesn't really matter. You just work with the magnitude, okay? You just work with the magnitude. It does not really matter when you get the signs in the force equation. Ultimately, the force sign will matter based on what direction is positive and what direction is negative. So let's say if the final answer that you get is 5 newtons, right? Minus 5 newtons, let's say. That is the answer you get between a positive charge and a negative charge. So if this is your answer, for the positive charge, the force will ultimately be positive 5 Newton, and for the negative charge, it will be minus 5 Newton. Why is that? Because the force on the positive charge is towards the right, and force on the negative charge is towards left. And left I have classified as negative direction, and right I have classified as positive direction. So for the positive charge, it's towards the right, hence positive 5 Newton. And for the negative charge, it's towards the left, hence the minus 5. So ultimately, this sign is not really giving me much. Okay. It is just there. It's a byproduct of plugging in the values. So don't worry about this. Work with this. And based on the direction you have set as positive and negative, work with that and decide which one has a positive force and which has a negative. Got it?
Yeah.
Perfect. So that is the force equation. I just gave you how to work with the force equation. Hopefully you have no confusion about the force equation. So the Coulomb law, in short, is written this way. And when I am drawing my force versus distance, it looks somewhat of this curve. Okay, so this is the force curve for, let's say, a positive charge. Okay, so if I bring a test positive charge, always remember, whenever we're deciding the field curve, like let's say electric field, E field curve, or electric potential curve, right? Or let's say you're drawing the field lines, right? So whenever you're drawing any of these for a specific charge, for one specific charge, let's say for a positive charge or for a negative charge, you draw it with respect to a test positive charge near it. So if I bring a test positive charge near a positive charge, it is going to be repulsive force. If I bring a test positive charge near a negative charge, attractive force. Okay. So similarly, that is how you draw the field lines. And I explained that above, that in case of the field lines for positive charge, it's outward. In case of the negative charge, it is inward. Why? Because we think with respect to a test positive charge. That is how we draw the field lines or
No,
any
said the
sort of
test is
curve. Yeah.
always positive. It's
The test charge is always positive. So you'll see this. Look at the definition over here. What is electric field strength defined as? Electric force per unit positive charge. So it is not that it is anything inherent with the topic. It is just how we define things. So we always define these definitions, electric field strength, electric potential, with respect to a positive charge. Okay, and then you will see this pan out again and again through the small subtopics that we have, that we are always thinking with respect to a test positive charge. What happens when I bring a test positive charge near whatever charge I'm working with? So what direction would the field line be at, or what will be the electric potential curve look like? So in all of those cases, we think with respect to a test positive charge, unless it's mentioned otherwise. But yeah, you'll see this as I move forward, you'll see what I'm talking about. Similarly, when you have this force thing, right? If I define the force over here, well, this direction has positive, this has negative. So it feels a force in this direction. I'll define this as positive. Okay, so when I bring a test positive charge over here, so as I was saying, with respect to this curve, when I bring a test positive charge near this positive charge, so what happens is as I move near the charge, the force increases, right? So it is the simple F is equals to K Q1 Q2 by R square. So as I decrease the separation, my force increases. So that is exactly what I'm showing over here. As I bring a test positive charge near this big positive charge that I have, my force increases. Okay, so the same would have happened if I had a negative charge. It is just that the direction of force would have been different. So if I brought in a positive charge over here, it would have, the force would increase increasingly as I would move closer, but the direction of force would have been different. So it would look something like this. This would be on the negative axis. Granted, I have defined left as positive and right as negative. In that case, this is how things would look like in terms of the force diagram. So the pink one is for the red charge, sorry, uh, opposite charges, and the white one is for like charges, that is same charge, right? So this is how the force curves would look like. Okay, the one where we have opposite, one we have same charges. Got it? Is this okay?
sorry, said can't hear you.
Yeah, you did you hear me?
No, I can't hear you, sir.
What's the last thing you heard?
Hello?
Yeah, can you hear me now?
Yeah, yeah.
Yeah, what's the last thing you heard?
The negative charge.
Yes. So basically, when you have opposite charges, the forces are attractive. So since this direction of force is what? Rightwards. So for this negative charge, if I had to draw the force diagram, the pink curve would be the force curve for the negative charge. Granted, I'm bringing a test positive charge from infinity to over here. Okay, so this pink curve defines the force curve for the negative charge. So this is the force will be attractive. So the net force for the negative charge will be felt in this
So
direction.
why does it
However,
like come
yeah,
constant, like sort of asymptote?
does it become an asymptote over here?
Yeah, why does it become?
So it's basically the nature of the formula. As you decrease the separation, the force increases with increasing magnitude. So if you y is equals to 1 by x square, if you plot it on a Desmos calculator, you'll see some this sort of a curve. Okay, since it's positive value, the values would be positive, something like this. This is how the graph would basically look like. On either side, it's trying to reach the zero, but it's not going to. Do you see what I'm saying?
Yeah.
Yeah. So it's basically the nature of the formula, and well, when we work with spherical conductors, you'll see there's a bit of a difference. What happens when we reach the surface of the spherical conductor and what happens inside the spherical conductor. So there's a bit of a difference over there, and I'll show that to you as well. But for now, if you're talking about point charges, this is
There's
how the
no
curves
electric
look like.
field. So
Sorry,
there's no electric field inside the sphere, I think, right?
in your spherical conductors.
Yeah.
Uh, yeah. So basically, they cancel out. Yeah,
All right.
the forces cancel out, right? So I just started off. I didn't talk about new stuffs. Electric field strength is the new stuff. You didn't miss much actually. I was revisiting some things. I was saying, okay, one new thing I did say. What would the field lines for the positive and negative charge look like? So for a positive charge, the field lines are always outwards. Okay, and for a negative charge, the field lines are always inwards. Why is this the case? So if they ask you to draw the field diagram of a positive charge or a negative charge, this is how it would look like. Yours should be much more neat, but I'm just drawing you a lump sum diagram. Basically radially inwards, same as you had in gravitational field. But point is, why is this the direction of the field lines? When I have a test positive charge, we always think with respect to a test positive charge. When we bring in a test positive charge, what is the force felt over here? Outward, because same charge. What is the force felt here? Outward, because same charge. So similarly, that is why we have an outward field line for the positive charge. Whereas for a negative charge, if I bring in a test positive charge, the force is inward. Force is inward. So field lines are inward. That is why we have the diagram as such as that, right? So that is one thing I talked about. The other is how does the force diagram look like? So for a positive charge, it is not necessary that you will have the graph on the positive axis. It depends on what side you define. Yeah. So yeah, it depends on what side you denote as positive and what side you denote as negative. It depends on that. So for a positive charge, it could be on the negative axis as well, depending on what side you're denoting as positive and what is negative. And the question will do it for you. You don't have to worry about that. Basically, over here,
Sorry.
if I define left as, yeah,
If we flipped the axes, what would it look like?
if you flip the this, or
No, if we
what are you
flip the
trying? What are you
axes.
flipping? Huh? Could you repeat?
Like, so right
If
now
I
we
say,
have force on the y-axis and the distance on the
ah,
x-axis, right?
okay,
Yeah, so what if we switched, we put a distance on y, it'll still be like the same, I think, right?
pretty much, yes. Not the same, no. So you're flipping about this y is equals to x line. It would look like this, but uh, something like that. So basically, the curve has a bit of a difference along the y-axis and a bit of a difference along the x-axis. It is not what do you call it? You learned it in Gen Maths, I guess. It is not symmetric about the y is equals to x line. That's what I was getting to. Yeah, you know what? I'll show if you since you've asked this, I'll show it to you. Where's my Desmos? Oh man, give me a moment. I'll stop sharing my screen for a moment, please. I'll show it on the Desmos. Uh, settings. Give me a moment. Where is this? Do not disturb. Restrict. Yeah, done. Screen. Oh, okay. So basically, our curve looks like this. Y is equals to whoop, 1 divided by, where's my division? X to the power of 2. Do you see this red line? This is what your typical force curve would look like, right? So it's a bit of a, I don't know, this is, you don't call this an asymptote, but anyways, basically you have this y is equals to 1 by x squared curve, right? And you're saying that if I flip this basically about the y-axis, sorry, y is equals to x line, what happens in that case? So you make, what would you have? And root over, okay, y is equals to 1 divided by, where's my root? Oh, x to the power of 1 divided by, this is so very confusing. Okay, do you see the difference? So basically, if you change the axis, this is what it will look like. The blue is the change. So you see how it's shifted more towards the y-axis now? This is what I was saying. Both aren't, I mean, not both the axes are not symmetric in nature in terms of how the graph curve leans towards the axis. So when you have this y is equals to 1 by x square, or f is equals to 1 by separation square, you have the red line, right? And it varies like that. And when you inverse the axis, then this closeness happens to be in the uh, y-axis. Got it?
Yeah.
Perfect. So yeah, I would recommend you guys playing with the Desmos calculator when you do work with graphs. It's a good skill to have. But yeah, that's the point. So this is how you have the curves. Now, electric field strength, which is the newer topic today. Uh, Electric field strength is the same idea as gravitational field strength. So when you talking about field strength and not the force itself, force is not equal to the field strength. Why is force different? Force is basically the net or total force on any amount of charge. More than one, less than one, doesn't matter. Field strength defines the force on 1 unit of charge, not 2, not 3, not infinity, not 0.2, just 1 unit of charge. What is the force applied on 1 unit of charge? That's the definition of a field strength. So basically, how do you find the field strength? Let's say I have 1 5 Coulomb of charge over here, one positive 5 Coulomb of charge over here, positive 5, positive 5. Now, how do you work with this? So let's say the force being applied on each other, right? This F1 is exactly equal to F2, right? The force on both will be equal and opposite, Newton's third law. So now, let's say I want to understand the field strength of Q1. Okay, so its field strength, if I had to define, if I want to find out what is the field strength at, let's say 10 meters away. So they are, let's say, 10 meters away from each other, the charges, right? From the center. I mean, it doesn't really matter. Those are point charges considered. So 10 meters away they are. And I want to understand what is the field strength at this position. Okay, so let's say right now the information I have is when I have 5 coulombs of charge interacting, I have a force, the net force of, let's say, 10 newtons. Okay, so this is the force I have when I bring in 5 Coulomb of charge, 10 meters away another 5 Coulomb of charge. So how do you find out the field strength at this position at 10 meters away? Any idea? Any idea?
Sorry, again, sir.
So my question is, right now the information I have is if I bring in 5 Coulomb of charge, 10 meters away from another 5 Coulomb of charge, I have 10 Newton of force on both Q1 and Q2. So how do I find out the electric field strength 10 meters away from Q1 due to Q1's charge? How do I find that? So how do I find the field strength? I know there's a 10 Newton force
10/5.
on 10 by 5, exactly. So if I want to find out the force per unit charge, then I'd simply divide whatever force I have 10 meters away divided by the charge itself. So that's the idea. Electric field strength of charge 1 can be defined as whatever force I have exerted by my charge 1 on charge 2 divided by the charge of 2 itself. So whatever the force is at this position divided by what amount of charge do we have over here that the force is being applied on. Okay, so if this was 5 Coulomb, then it's going to be 10 by 5. If it is 3 Coulomb, then 10 by 3. So basically force by whatever amount of charge I have over here. So point is force divided by my test charge. Okay, what is this? If I'm trying to understand the electric field strength of this charge, I'm going to divide the force divided by the test charge. Okay, the other charge that I have. Granted, I'm analyzing the field strength of the white concentric circle one. Okay, so basically the equation would look something like this. And this is what I was talking about initially, that not this electropotential equation is also similar. But yeah, this is how the equation turns out. You have the force equation, KQ1, Q2 divided by separation square divided by my test charge, okay, which is not 1 Coulomb. So I divide both and I have ultimately KQ1 by R square. This much, are you good with that idea? Are you clear on this?
Yes.
Perfect. So basically what this tells us, if I have a random charge, positive charge, what is the force exerted on 1 Coulomb of charge 5 meters away? What is the force exerted on 1 Coulomb of charge 10 meters away? What is the force exerted on 1 Coulomb of charge 15 meters away? All of this information I can find by plugging it over here. What do you plug in? So to find out the electric field strength of this positive charge, I say K, which is a constant, times whatever the charge this positive charge has, let's say 5 Coulomb, divided by the separation. So I want to find out the force exerted on 1 Coulomb of charge 5 meters away, so 5 square. Let's say I want to find at 10 meters away, the 10 square. Let's say I want to find at 15 meters away, then 15 square. So that is how it works. In all cases, you find force exerted on 1 coulomb of charge. That's what field strength is. Hopefully that much you're clear on. And what is the unit going to be? You had force by charge, so Newton per coulomb. This is also valid, volt per meter, volt per meter. And why is this valid? As you can see, it is covered later, and I'll talk about this. There's a good reason for this, and I'll show it to you why this unit is also valid. Now look how the electric field lines would look like if I have uniform field lines, okay? Or I have the same field strength across a given space. Now, if you remember correctly from gravitational fields, I talked about something uh, that is, tell me this. I'd position this 1 and position this 2. Is the field strength in these two cases different of the field strength due to the positive charge? In both of these, position 1 and 2, are they different?
So if it's uniform, it's not.
No, I mean, do you think it's uniform? Are the field strength uniform around the positive charge over here? Looking at the field lines, the white lines are field lines. Do you think it's
Yeah,
uniform?
it is, yeah.
Yes, it is. So here's the thing: how do you identify if the field lines are uniform?
They'll be passing through the center perpendicular to the surface like that.
Nope. So you see if the field lines are moving away from each other or having a constant distance away from each other. So look at this. Near the positive charge, are the field lines closer together compared to away? Yes. So over here, the distance between the field lines is small. As you move away, let's say 10 meters away from the positive charge, the field lines are more apart from each other. Okay. They're more separated. So over here, the field strength is weak. Is what? Weak. That is why the field strength between 1 and 2 is different. Okay. Why is that? 2 is at a position where the field lines are more apart, more apart. And 1 is at a position where the field lines are closer together. So this is not uniform. Non-uniform field line. Okay. So what you're saying is, like for field lines, this is the basic property of field line, that they will be radial and intersect through the center. So any field line for a point charge, that is basically the definition for anything that can be considered as a point charge, that my field lines will cut through the center of the circle. Okay. So that is the point mass approximation that you were talking about. Valid. But in this case, to understand if the field lines, if the field strength is constant or not, we look at the spacing between the field lines. Got it? So if the spacing is increasing, that means field strength is changing or different. Okay. So I'll ask you another one now. This is position 1, and this is position 2. Are the is the field strength between these two positions same or different?
Same.
Same. Perfect. So why is that? Because the spacing, look, is same across everywhere. So the conversation is about the spacing of the field lines. Since the spacing is same across the board, it is uniform field line. We call this uniform fields. Okay, how did we get this? We looked at the spacing. It doesn't matter if this point is near the positive plate or near the negative plate. Doesn't matter. That's not the conversation. The conversation is, are the field lines. The field lines denote the strength of the fields. When you have a higher density of field line, that denotes higher field strength. Okay, one more last question I would bug you guys. Compare these two. Are they different or same? Field
Different.
strength. Different. Which one? Mark it. Which one is higher field strength or higher force would be exerted? 1, 2.
Two.
Perfect. Perfect. Yeah. So at position 2, you have a high density of field line. And that denotes that over here, I have a higher force being applied. And since the field strength is greater, I've written over here, but anyways, so that is the core idea. Okay, that is the core idea. We denote field lines for that reason, and that is why with spherical field lines, they move away from each other, because as you move away from a point charge, this is how the field lines separate from each other. Hence, the force decreases or field strength decreases. Got it? So that is a difference between a plate charge and a point charge. So if you have plates like this where the charges are uniformly distributed, doesn't matter where you put a charge in between, here, 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 it will face the same force. It's a 10 Newton of force everywhere in between the space. It feels 10 Newton of force. Let's say you have non-uniform plates like this, and you have an uneven accumulation of charge on one end, another uneven accumulation of charge over here, right over here. So what happens in this case? Different force here, different force here, different force here. Great. Now, the other thing that you guys need to know is when you have opposite charges, right? When you have opposite charges, how do the field lines flow? How do you draw the field lines? So you see a model example over here. This is exactly how you should draw in your exam paper. Let me draw again. The first thing, the field lines goes from positive to negative, similar to your convention current law. Okay. What do you know about conventional current law? Flow of current, that it goes from the positive to the negative. Okay. So similar logic over here. We draw the line from the positive end of positive charge to negative charge. Okay. So now, as you move away, why is this bent? Why is this bent? Right? The question can arise, why is this bent? Well, it's simple. When you have the forces individually, charges individually, sorry, the field lines look somewhat like this, right? This is how the field lines look like when they're separated. So they're infinitely away from each other. What happens when you bring them close together? Basically, the field lines want to join, right? The field lines will now join together. So this one joins, becomes like this, and this one joins, become like this. This one joins, become like this. So do you get the idea of why these are curved line looking like this? Basically, the field lines are joining together and making one route from one end, one point to another. Another thing I will mention that is a very important thing when drawing the field lines, never have your field lines intersect another field line. Never draw something like this, where another field line is crossing another field line. One field line is crossing another field line. Never do this. Wrong, mistake, you lose marks. These are simple marks. These questions of drawing field lines between charges are simple and very easy marks. Do not lose your marks over here. So very few things to note as you move away from the charge, right? From positive or negative charge, the spacing between the field lines increase. When you're towards the charge, spacing is less. When you're away from the charge, spacing is more. Okay. And you have, except for these horizontal lines, the lines will be curved, somewhat curved like this. So this is a bit of a model example. Follow this diagram and you'll be good. Okay. So this is how you have the field lines, okay, between a positive and negative charge. Okay. Hopefully no question till now. Now, next topic that we're going to traverse into is electric potential energy. This is, you can draw a parallel with gravitational potential energy topic. If you remember that, it will be easy to understand. So conversation is gravitational potential energy. So what happens in electric potential energy is the same logic. If you remember from
Sir,
gravity, yeah, go ahead.
is
Yeah.
electric potential energy and electric potential the same?
Nope. Electric potential is with respect to 1 coulomb of charge. The energy needed to bring 1 coulomb of charge from infinity to a defined point, and electric potential energy is basically any coulomb of charge. So whatever energy is needed to bring 10 coulomb of charge to bring from infinity to a defined point, we say that it's electric potential energy. And when it's 1 coulomb of charge, we say it's the electric potential. Got it?
So for 1 coulomb of charge, the electric potential is equals to electric potential M.
Sorry, can you repeat?
For one
For one
coulomb
coulomb
of
of charge?
charge, yeah,
Yeah.
the electric potential is basically the same as electric potential energy. It's
Yeah,
electric
yeah, yeah.
potential.
Yeah, definitely. Yeah, you're right. So yes, I mean it's just the way of putting things, defining things, and you'll see
So it's the
why.
same in gravitational as well. Gravitational potential and GPE, that's the difference.
Yeah, exactly, exactly. It's just, that's why I said is you can draw parallel with that topic and understand everything here as well. It's the same thing. It's just that we have the notion of repulsive forces in electric field. That's the only difference. Otherwise, it's the same thing. Okay. So if I go on, you will see, by the way, this U symbol denotes energy, electric potential energy, or even gravitational potential energy. That denotes potential energy in general. But yeah, when you have, let's say, the electric potential energy, if I have to define it for you guys, it is the work done in bringing a charge from infinity to a defined point in an electric field. What does this mean? In brief explanation, if I have Q1 over here, and this is the charge that I'm going to analyze. Okay, this is my charge that I'm analyzing. This is, let's say, positive charge, and this is also a positive charge. Okay, so I'm bringing this Q2 from infinity to a defined point R, right? And what will the work done be in bringing this positive charge from infinity to R? Okay, and what do you think? Will the work done be positive or negative? So the question is, will the work done be negative or positive? Bringing it from infinity to R. Both are
Positive.
positive charges. Note that. Exactly,
Okay.
positive. Because they're repulsive, right? So I'm putting my mechanical energy into this Q2 and bringing it to R. Got it? So I'm giving it my energy. So work done is positive on this. So now, going on with that idea, right? Going on with that idea, what is the force diagram going to look like for this? I mean, for both of these charges. Basically, when the charges are close together, the force is really high. Okay. When I increase the separation, it decreases with a proportion of 1 by r squared. With that proportion, the force decreases. So are you okay with the force curve? Is this okay? Yeah. Do you understand
Yes.
the force curve that I have drawn? Yeah. So now the conversation is, how do you find the electric potential energy? Remember, where do we go from? Infinity to R. So over here. So we are going to integrate from infinity to R. Got it? Why? Because work done is force into distance. And when you're integrating, you're multiplying the y-axis with the x-axis, right? So the shaded area under the curve is the total work done, right? So now let's derive the formula. I'm going to integrate the force from infinity to R. Okay, infinity my starting point, R my ending point. What am I integrating? The force equation. Q2. That's what this I'm integrating from infinity to R. So now, and I'm integrating with respect to the R, of course. So one question that you guys will have is, might have, is why is this minus sign here? Even if you don't have it, it is not wrong. Wrong as in it's not a problem, but I have this negative sign over here because you're bringing the positive charge, granted both are positive charges, that is what we have set. I'm bringing this closer. So I'm working against the force. The force is outward, it is repelling each other. So if I think with respect to the positive charge, it's repelling it. So outwards, and I'm bringing it, the distance or the movement is happening in the opposite direction. So my force and the movement are opposite. Okay, my force and the movement are both opposite, which is why I have this negative sign over here. While the change is happening in one direction, the force applied is in the other direction. So that is why, to respect the direction, I have a negative sign. Now, another way to explain is, which is, like you could say it's a cheating way of explaining, is in the ultimate equation, I don't want a negative sign over here. Okay, I don't want a negative sign over here. I'll explain why. So I don't want a negative sign over here. So while doing the integration, I'm including a negative sign over here. So the negative sign gets cancelled off. And ultimately, this is the equation I get, which is a more neat and useful equation. Okay. So that's one way to explain as well. I'll explain why I don't want the negative sign. Now look, when I'm integrating from infinity to R, and I'm going to take all the constant outside of the integral because I can do that. You can move the constants out. So you're left with this. And now you have to integrate 1 by R squared, which I would like to believe most of you guys can. So R to the power minus 2 will be R minus 2. I'm sorry, R minus 1 minus 2 plus 1 should be R minus 1 divided by minus 1. So ultimately you get 1 by R. Okay, minus 1 by R. So this is what you get ultimately. And you still haven't put in the limits, which we will. So when you put in the limits, it becomes minus 1 by R minus 1 by infinity. Okay, so ultimately the answer will become simply minus 1 by R. Okay, this part is 0 and you're left with this. So you're left with minus k q1 q2 times minus 1 by R. So this minus and this minus gets cancelled off. Ultimately you're left with this. Got it? So this is why you get a positive expression over here. Now why is this a neat equation? And I was talking about this towards the beginning of the class as well. The reason it's a neat equation is because if I have positive and positive charge over here, what is the electric potential between them? Positive or negative? Quickly. Between the positive and positive charge. Positive or negative?
What? It will be positive.
Yeah, the electric potential energy I asked. Yeah. EPE, positive or negative. So it will be positive. If I have negative, what will it be?
Negative.
Perfect. So now notice over here in this equation, if I put in two positive values, k times plus 5 times plus 5, let's say plus 5 is the charge, the answer, the u that I get is positive. So it gives me directly the right answer with the right sign. If I plug in minus charge, minus 5 times positive 5, that is two different charges, I get a final answer that is negative. So when I have opposite charges, it's attractive force, hence my answer should be negative. And this equation also gives that. That is why it was important to express the equation in this form without the minus sign over here because it's more useful. That's great. Now, how do I find the change in electric potential energy? What did I find till now? That if I have a positive charge, and let's say another positive charge, and they are separated at a distance 10 meters away, what is the electric potential energy of this charge or this charge? Both will have the same electric potential energy. Do you guys understand why they will have the same electric potential energy? Yes or no? Yes?
No.
Yeah. So the thing about the electric potential energy is, well, let's say it's in space, and these are the only two particles in space, okay? If they are, and we are in space, as in there is no end to space, there is no other particle, and they are somewhere about nowhere, since it's space and it's infinity, there is no defined point in space. We can't really consider any position as 1 meters away, 2 meters away. Whenever we say 1 meter away, it's from something, right? The notion of distance is valid if I have a reference point, right? So when we talk about this, we say from infinity to a defined point over here. So we consider infinity a reference point. And you will hear this from certain teachers if they're teaching this topic to you. Okay, so the point of infinity is to establish a reference point. Now, why is the electric potential between two positive charge the same? The EPE of this will be, let's say, 5 joule, positive 5 joule. The electric potential energy of this will also be positive 5 joule. Why? Because if in space you just have these two positive charge, let's think about Q1 and let's say this is Q2. What is the electric potential energy of this? By definition, it is the energy required to bring this charge from infinity to this defined point. Okay, to this defined point. And what will that energy be? What will that energy be? 5 joule. And again, for this, if I have to bring it from infinity to a defined point, is it not going to be same? Yes, it is. It is going to be same. Let's say I have different charge, different amount of charge. Let's say Q2 is 10 coulombs and this is 5 coulombs. Okay. Even then, their electric potential energy is same. Is what? Is same. Why is that? Let's say both of them are going to have now 7 joules of electric potential energy.
Sir,
Why? Yeah. Yeah, go ahead.
see that when the source is negative, um, the work done is negative. So that means energy is negative.
Source is negative as in?
Like,
It's not about negative or positive. Is it attractive force or opposing force? If it's
yeah,
attractive force, your potential energy becomes negative.
yeah, but don't we say that energy is a scalar quantity, so it can't be negative?
Okay, that's a different thing. That's a different thing. I was supposed to explain this to you. I don't remember if I explained. We are not talking about energy over here. What is the definition of electric potential energy? It is the work done in bringing something from somewhere to somewhere else.
Yeah, so
And
it's the
this
energy
by
used.
definition means something else. Yeah.
So it's the energy
Well, what
used,
is,
right?
yeah. So it is about is the energy given or taken? Energy is not positive or negative. It is in your remember in ideal gas you had Q plus work done. This Q thermal energy can exit the system or get into the system. Energy is negative or positive. It is simply denoting is the energy leaving the system or getting into the system. Energy is not negative or positive. It is a scalar quantity. You're right. That's a really, really good question. I'm glad you asked this. I was supposed to clarify this. Someone else also asked this too. Point is it leaving the system or going into the system? What is happening over here? Is it what kind of transfer is over here? That is what we denote by the positive and negative sign. Not that the energy is positive or negative. Energy is scalar. It has no direction attached to it. It is simply the transfer we denote. So similarly, when we have this attractive or repulsive force, in what direction is the work being done? In the direction of attractive force, so we're bringing them together, or opposite to the attractive force, or in the direction of like opposite to whatever force is being applied. So like in case of repulsive force. If the force is outwards, I'm working opposite to that force, so towards this positive charge. So the transfer of energy in this case is positive. And when I have unlike charges, the forces are inward. And the transfer of energy is not happening in my case. I'm not transferring anything to this. It is simply losing all the energy I had once transferred to it. So over here, the work done is negative when it is opposite charges. Do you get the idea?
Yes.
Yeah. So the moral of the story is we denote this positive or negative as transfer with respect to something we're having this conversation. Is it leaving the system? So in case of thermal energy, the system is the reference. Is it leaving the system or going into the system? That is how we get the positive or negative. Similarly over here, are we working in line with the force action, or we're working opposite to the line of force? That is how we get the positive or negative. Okay. Similarly, not similarly, but the conversation that we were having over here, why do they have the same electric potential energy, regardless of the fact if they have different or same charge? The thing is, if I bring, let's say one is 10 Coulomb, the other is 5 Coulomb, and I bring this positive charge from infinity to this defined point, right? What happens? I have done some amount of work. What amount of work? I've basically, if I plug in K, Q1, Q2 divided by R. So what is one of the charge? 10 Coulomb. What is another charge? 5 Coulomb. What is the separation I am bringing at? 10 meters. Okay. Similarly, with this charge again, U is going to be K times 5 Coulomb times 10 Coulomb. What separation am I bringing at? 10 meters. Isn't the expression same in both cases? Yes, it is. In both cases, regardless of what the charge is, it's the same. So electric potential energy, if I just say that let's say, finding with respect to this charge, I'm bringing this charge from infinity to this point, and I've done 7 joule of work done on it. The electric potential energy of this will be 7 joule. Similarly, the electric potential energy of this should also be 7 joule. Okay. It doesn't matter. You could leave this and bring this from infinity. Same work will be done. Does not matter. Okay. That is why in a system, in an isolated system, whenever you have two charges, okay, whatever the electric potential energy of this is, same charge, same energy of this one as well. Same. Okay. Fair. Clear?
Sir,
Yeah.
in questions, it will be mentioned whether or not it's like isolating, right?
It will always be isolated. Otherwise, you can't really work with the question. They won't ever give you more than two charges. They won't give you more than two charges or more than two anything. They will say these two charges are isolated. Otherwise, think of this. You have the solar system. Sun is in the middle. Why have I drawn the plus sign? Sun is in the middle. You have multiple orbits. Earth is here. Mercury, what have I drawn? So there's other Mars and everything. What is the gravitational potential energy of the sun? What is it? You can't say, give a simple answer. It is impossible. You can give an approximation. Why? Because you have to consider gravitational potential energy between this system, that is this planet and this, I mean, sun, and then again add with that Mars and the sun's gravitational potential energy, then add with that the gravitational potential energy of Earth and the sun. So if I have to find out the gravitational potential energy of sun, I have to add an infinite amount of interaction that sun has with infinite amount of objects in the universe. It's not possible. So whenever you work, and it's more complicated than that. It's not as simple. So point is, you will always be given an isolated system with two particles or two masses or two charges. Got it? This is ideally which what should happen. Okay.
Yes.
Okay. So that is the conversation of having a
So
system.
basically, whatever amount of energy one of them possesses, they both possess the same energy.
Yeah, exactly. They will both have the same
Is
energy.
it they both possess the same energy, or like for example, when the charges are
They will,
alike, um,
yeah, they will
it's
both have the
constant,
same potential energy.
or do they lose and gain the same amount? Like,
No, 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 no. So if I'm talking about this system, you were probably thinking this is losing 5 joule of energy and this is gaining that same 5 joule of energy. No, that is not the conversation. That is not what's happening. The energy conversation is basically, since it's, you have to steer away from the charge notation over here. You can't talk about the charge, what charge they have. Conversation is, are the opposite charges, are they attractive forces? That is the conversation. They are attractive forces attracting towards each other, hence negative potential energy. Both of the positive charge and the negative charge doesn't matter. They have and negative electric potential energy. Why? Because they're attracted to each other. So that is the potential energy of the system, right? So it just denotes that if I had to bring this from infinity to over here, the amount of energy that would have been lost. And if I had to bring this from infinity to here, the amount of energy that would be lost. That is the definition of electric potential energy. So it's not a gain of this and then a loss of this. It's simply what work done was done on both of these particles, I mean, charges. Correct?
yeah,
Okay. So now, how to find the change in electric potential energy? Till now, we had a conversation where we were bringing one charge near another charge from infinity to a defined point. Okay, this is infinity. So till this point, let's say. Now, point is over here. I don't want to mark or understand the EPE. I want to understand that. I want to know that. Let's say from for Q2, you know what? I'll give it a charge. So to bring 5 Coulomb of charge from infinity to R, let's say this is 10 meters. Let's say to bring it till R, I did 20 joule of work done. Okay. Now, I want to understand that what amount of change in energy happens between R and another distance R, so R2. I don't want to know what energy was, what work was done in bringing Q2 from infinity to R2, but I want to know what is the change in energy that takes place between going from 10 meters to 20 meters. So I just want to know that. How do I find this change in energy? How do you think? How would you go about this? So I want to know what is the change in electric potential energy in going from R1 to R2. Any idea? No?
We
Okay.
find the
So
energy from,
yeah, you're on the right track, yeah?
we find that both the energies like for 10 meters and for 20 meters, and then we subtract.
Perfect. That's the core idea. So you find the electric potential energy uh, at R1 and you find the electric potential energy at R2 and then subtract. So ultimately, whatever the value you do get, it can be positive or negative depending on if you're going from R1 to R2 or going from R2 to R1. Granted, these are both positive charges. If I'm going from R1 to R2, will the energy be lost or gain? Will the change in energy be, oh my God, will the change in energy be positive or negative? Granted, I'm going from R1 to R2 and I have two positive charges. So separation is increasing. What do you think is going to happen? Is the change of energy going to be positive or negative? Are you going to lose energy or gain energy?
Lose energy.
Think about it. Perfect.
Negative.
You're going to lose energy. Yes, negative. So why is that happening? Because the forces are actually outward, right? So they're repelling each other. So some amount of work was done to bring the charges close together. So we pushed it in. Now, when both the charges are going in the same direction as the force uh, is directing towards, then losing that energy that I transferred to it. So it's a loss of energy because it's losing its energy to go towards the line of force, right? Go in the direction of line of force because it is outward force and they're being pushed away. Okay. So it is losing whatever energy was put into it to bring close together. So that's the core idea. And I can uh, translate that idea into an equation. So you have the idea, right? How do you prove an equation? So if I go from R1 to R2, so R1 to R2, which is in line of force of action, what happens is it's the same integration. I take the constants outward, outside, and I integrate. 1 by r square will become minus 1 by r. So this, then I put in the value minus 1 by r2. That is the final position minus the initial position minus 1 by r1. I open the brackets. You're left with minus 1 by r2 plus 1 by r1. So I take the plus 1 by r1 in front and I take the minus 1 by r2 later. Okay, so you're left with this equation. This is the change of electric potential energy. This is what? Change of electric potential energy. Do we get the idea over here? So what's happening over here is, let's say you're going from R1 to R2 to R2. You put in the values, very simple, and you plug in K, Q1 and Q2 and you will find the change in electric potential energy. Now I want to make your lives a bit easier, and before you get confused in the exam or in the class test and they tell you, or you have a tough time finding that what distance is R1? Is it the distance that is closer or is it the distance that is further away? Okay. So you probably in the exam hall, a lot of people have done this or gotten confused that which distance do I put in R1 and which distance do I put in R2? My answer to that is doesn't matter. It literally doesn't matter. And I'll tell you why. You can put in this further away distance, that is, if you're going from R1 to R2, you can put in R1 over here, R2 over here. Or if you're going from R1 to R2 and you want to put in R2 over here, okay, fair. And you put in R1 over here. Does not matter. And I'll tell you why. The value that you ultimately get will be positive or negative. That is the only difference that you're going to get in the value. Okay, that is the only difference that you're going to get in the value. And it doesn't matter. Why does it not matter? Because the thing is, you should intuitively know, is my change supposed to be positive or negative? Like I asked towards the beginning of the question, that going from R1 to R2, granted both are positive, will there be loss of energy or gain of energy? And your answer was loss. So change should be negative. So regardless of the fact that the answer comes positive or negative, you will just change the sign and your final answer will be negative. That's it. You know why I say this? That is because there is no one way of expressing the equation over here with a minus sign or without a minus sign that will always work. There is no way of expressing this equation. I have expressed it this way because, that's how the integration happened and this is the expression I got. But it doesn't matter which distance you put in here or here, the one closer or the one further, doesn't matter. You simply get the answer, that is, whatever the initial position is, let's say you put in here, whatever the final position is, you put it there. Whatever answer you get, you see the text, you see the question and analyze that, is it supposed to be a loss of energy or gain of energy. Based on that, you change the sign. Okay, if it's already positive, great, and if it's supposed to be negative, you change it to a negative sign. So use your logic and save some time. Okay, a lot of people just ponder over here for 5-10 minutes. Which distance do I put in at R1? Don't do that. Do the question. Whatever answer you get, you change the sign based on what your intuition, what logically you should happen. Okay, you just read the question. Okay, save your time. Now, I have explained this extensively till now. What is positive electric potential energy? What is negative electric potential energy? By now, you should understand. Whenever you have positive electric potential energy, it means repulsive. Your repulsive force. So you have like charges interacting. They want to push away from each other, but externally a force has been applied that they're close together. Hence, they have positive. Same with two negative charges. Even though I don't talk much about two negative charges, it's the same case. Give me a moment. It's the same case. It's going to be positive as well. So when is it negative? When you have opposite charges. Okay, when you have opposite charges, they're attracted towards each other, and they're going to be like, I want to go towards each other. I want to go towards each other and get smooshed up, but I'm stopping them from going towards each other, right? And in this case, this is attractive force. Hence, the electric potential energy is negative. Why? Because bringing it from infinity to this point, it basically lost energy. Because when I had put this negative charge at infinity, I personally did all the work, transferred the energy to the negative charge, and took it to infinity. Now, when this negative charge came from infinity to this separation, it basically lost that energy. And we know at infinity, the energy is 0. So if you lose energy from 0, what is the value? Negative. Okay, so that is why EPE in like charges in attractive force is negative. Very simple. Now comes the conversation of electric potential.
Sir, could I take a screenshot of the part of blue page?
This?
Yeah.
Okay.
So could you zoom in a bit more?
Zoom out or zoom in?
Yeah.
This part or the latter part?
Then Albert, let's take a picture of this.
Okay.
So could you go down a bit now? Okay.
Yeah. So now the conversation is electric potential. We talked about electric potential energy, and it's the same conversation again. That we consider electric potential to be with respect to 1 coulomb of charge. Now, electric potential, I will say, maybe there is a good diagram over here. Okay, I'll use this. So if these are positive charges, whoop. Now, whenever you have electric potential, right? Not electric potential energy, we have a conversation with respect to one charge. Okay, so if this is the charge we're analyzing, then whatever electric potential value we get is only of this charge. Unlike we had just had a discussion of electric potential energy, where if I have two charges and EPE for this is 3 joule, what will be of this? It will be 3 joule as well. Same. But you can't say the same with electric potential energy. Sorry, electric potential. Because if this is 5 coulomb and this is 30 Coulomb, the electric potential of either of them are going to be different. Not the same. Not the same. Okay? Not the same. So in this case, for let's say them being separated at 10 meters away, right? What is the electric potential of the positive charge at 10 meters away? Can you tell me? Of the positive charge 10 meters away. What would you think we have to do? So I'm trying to find the electric potential of the positive charge at 10 meters away. So what is the work done for 1 unit of charge to bring it from infinity to this 10 meters away position? Right now, to bring this 30 Coulomb, we have done 3 joules. Not sure? Okay. So now, if I just show you the explanation over here, deriving the electric potential is the same as we did before. Whenever you found the electric field strength, what was the conversation? You found out what is the force exerted on the other charge. So if you have Q1 over here, Q2 over here, they're 10 meters away. What is the force exerted on this? 20 Newton, let's say. So what will be the electric field strength at this position? Granted, this is a 5 Coulomb of charge. 20 divided by 5, which will be 4. So the electric field strength 10 meters away from Q1 will be 4 newtons per unit of charge. Okay, 4 newtons per unit of charge at 10 meters away. It is going to differ at this distance, which is, let's say, 5 meters away, and so on and so forth. For other distances, it's going to be different. The point is, you basically divide the test charge. So the electric potential will be given by whatever the electric potential energy is divided by whatever my test charge is. So in the previous example, if I denote it over here, I have 5 Coulomb of charge here and 10 Coulomb of charge over here, right? And they are at a distance, not infinity. Let's say this distance is 10 meters. I want to find out what is the electric potential of Q1 at 10 meters away. How do I do that? From the information I have right now. I mean, I don't have all the information. Let's say the electric potential energy of both Q1 and Q2 is 10 joules. 10 joules. So they have the same electric potential energy, but I want to find out what is the electric potential of Q1 at 10 meters away. How do I do that? The electric potential of Q1 will be given by whatever the EPE is, 10 joules, divided by whatever my test charge is. And that is how much Coulomb? 10 Coulomb. And my electric potential is going to be 1 joule of energy per Coulomb, right? 1 joule of energy.
You just divide by the total charge to find. Okay.
Yeah, so you're dividing the charge of the test charge. Yeah. So basically, in this case, the electric potential of Q1 at 10 meters away is 1 joule. Let's do the different one. Let's do why did I erase that? Let's do of Q2 at 10 meters away. So it's still 10 meters away, but in the opposite direction. And let's say it does have 5 Coulomb of charge, and my Q2 has 10 Coulomb of charge. So how do I find out of Q2? Any idea? Now what do we do? I want to find out the electric potential of Q2 at 10 meters away. This is my test charge now. Okay, so what we will do is, since the electric potential energy is 10 joule as well, in either case it's 10 joule, potential energy doesn't change, potential changes. So electric potential energy between them is 10 joule, and it is being applied on, or it is being said with respect to a 5 Coulomb of test charge. So we divide by 5 and we say, well, it is going to be 2 joules per Coulomb for the Q2. And it's simply logical. Why is this logical? Why does this make sense? By intuition. I'll explain it to you. If my Q2 is a larger charge, which I have denoted, yes, it is, which is 10 Coulomb of charge, to bring any 1 Coulomb of charge, 1C, positive, let's say, any 1 Coulomb of charge 10 meters away, the amount of energy, the amount of work that I need to do is more. How much more? Twice as much more, because it's 10 Coulomb, right? So I don't need to do 1 joule of work, I need to do 2 joules of work, because it is 10 Coulomb of charge. Now, if I have this 1 Coulomb, 5 Coulomb of charge, and I'm bringing a test 1 Coulomb of positive charge from infinity to 10 meters away, I do 1 joule of work. Okay? So the thing is, electric potential for different charge will be different. Okay? Unlike electric potential energy, granted they are together in an isolated system, they will have the same electric potential energy. But electric potential is individual to each particle, each charge. Same with electric field strength. Same with electric field strength. The force exerted on both the particles is same. Q1 and Q2, the force they experience is same. But the field strength of both are going to be different. So the field strength of Q1 at 10 meters away will be weaker as compared to the field strength of Q2 10 meters away. Because Q1 has 5 Coulomb of charge and Q2 has 10 Coulomb of charge. So the force per unit charge for Q2 at 10 meters away will be larger because charge is larger. And we are talking with respect to 1 Coulomb of charge. Are we getting the point? Yeah. So electric potential is the work done per unit positive charge in bringing a small test charge from infinity to a defined point. Okay, fair. So it's the same thing. You have potential is basically EPE, electric potential energy, divided by the test charge. So what is my equation for electric potential energy? This K times Q1 times Q2 divided by R, divided by whatever my test charge is. So Q2 and Q2, test charges get cancelled off. You're left with this. So simply by this equation, you can find out what is my potential at different positions. That is to say, if I have a Q1 charge over here, of any charge, doesn't matter, 5 Coulomb, 10 Coulomb, 100 Coulomb, doesn't matter. For every single position, I can find out what is the potential energy of 1 Coulomb of charge. So how much work will be needed to be done on 1 Coulomb of charge to bring it 15 meters away, to bring it 10 meters away, to bring it 5 meters away. And now that you can multiply with any Coulomb of charge. So if you know the electric potential at all of these positions, and I ask you what is the electric potential energy going to be for 5 Coulomb of charge, can you answer? Yes. Whatever the electric potential is times 5. That will be the electric potential energy. Okay? That will be the electric potential energy. So now, hopefully, that is clear how we find the electric potential. And now, how do you find the change in electric potential? Same thing. You have the change in electric potential energy equation, KQ1, Q2 times 1 by R1 minus 1 by R2. This you will divide by the test charge, that is Q2, and you're left with this equation. Same thing, you divide by Q2. That's it. This is the change in electric potential. So if I have a charge being analyzed over here, Q1 with 5 Coulomb of charge, what is the difference in electric potential going from 10 meters away to go to 15 meters away? What is this delta? What is this change in electric potential that you can find using this? That is how much work is done to bring 1 Coulomb of charge from infinity to here, and then how much work is done to bring 1 Coulomb of charge from infinity to here, and then the difference between both the work done. That delta, that difference of work done, is expressed by this equation. So that's the change in electric potential. So now, how do you plot the graph? This is how you plot the graph. You have a typical y is equals to inverse x curve. So this, right? And how is this different to the field strength curve? So the potential is, it's just, if I show it on Desmos. So you have y is equals to 1 by x squared. This is 1, right? And then you have y is equals to 1 by x. Okay. So the difference is, the simple difference is, one is more steep, the other is less steep. So the purple one, if you see, is going to be a bit less steep. And then the green one is a bit more steep in nature. So it's just how they are on the axis. So if you find out the gradient, you will see there's a difference in the gradient at each position. Okay, so you can also say that it is to an extent the inverse of each other. So if you draw a y is equals to x curve, okay, so they're about, you could say they're symmetric about this. Okay, so now, okay, no, they're not symmetric. What am I saying? Y is equals to x, if I make x root over, no, they're not symmetric. It would have been symmetric if it was 1 by root of x. Anyways, point is, one is more steep, the other is less steep. Okay, so that is the core difference. When you plug in a few values over here, though, it may be a bit more visible. 200. Whoa. 200 to 2 over here. So if you just notice over here, one is more steep, the other is less steep. So look at the purple and the green line, right? So that's at core what the difference is in terms of having 1 by x and 1 by x squared. You will also see a difference in terms of there is a number of curve on the negative gradient, that is what negative quadrant as well. So you have one on this side. I don't know if you can see my cursor over here. So you have one on this quadrant and one on this one, second and third quadrant. So there's a difference over there as well, but that is not needed for you guys. You just need to notice the first quadrant. Yeah.
What are these graphs of what again?
Sorry, what are the dots?
No, what graph is this? This is electric potential or potential energy?
So electric potential and electric potential energy is pretty much the same. It's just you divide by the test charge.
Yeah, I'm
So
saying what is this graph of? Like what you're showing right now?
so the one that is purple right now is the electric potential, and the one that is green is electric field strength without the constants.
Electric potential against distance or
Distance. So electric potential against distance, electric field strength against distance. So I'm just showing you the nature of the curve, how they differ.
Here, I also wanted to ask is like electric field and electric field strength is the same, right?
Well, yeah. I mean, if they just say electric field, it just
Yeah, like
means
if they
electric
say
field
find
lines.
the electric field, or if they say find electric field strength is the same, right?
I couldn't say because they should say electric field line in that case. Define electric field lines, or yeah, they could say electric field. So you just talk about. Did you see this in a? Is this a 2 mark question?
Yeah.
Yeah. So you will say this is. It is a region of space where two charges interact and there's a force between them. So it's a region of space when two charges interact and there's a force. So it's basically talking about the space where the field lines exist. So electric field is caused by two charges interacting. So you just answer as two charges. When two charges interact, it is a space when two charges interact and there are like field lines going between the positive to negative or outwards, depends. If you're talking with one point charge, you can just say with respect to a test positive charge, it will be an outward field line. So you can also add that. But yeah, it's simply a region of space. Okay. Did you see the mark scheme answer? Yes.
Yes.
Yeah. So what does it say? Is it what does it say? Is it a region of space where two charges interact and there are field lines, or what?
It said, you mean the question I'm talking about, sir?
Yeah, yeah.
It said define electric field at a point.
Okay. And what does the mark scheme say?
Said it is the force per unit charge experienced by a positive charge placed at that
Okay.
point.
Okay. So then it's asking about electric field strength then. That's why you asked me this, right? Because
Yeah.
it's saying force per unit charge. I get
Yeah.
it. I get it. Now I understand. So the thing I was explaining is also like I remember answering that as well. So the question was, I don't remember the exact question, but it says it was 2 mark question as well. So define electric fields. So the question went something along this. Define electric field. So and then the answer is somewhat like it's a region of space when two charges interact, a force is applied on each other. So that's how I would go about answering that. Now, the one you said, uh, which is electric, what define electric field about 1 point, I guess, something along those lines. So in that case, they're asking about electric field strength on a point charge. So I guess it's you have to understand the context of it. Okay, so it can be both. Actually, it can be both because they can just blatantly ask you what electric field is, and you might have to explain that. Then you talk about it being a region of space XYZ. Okay.
Yeah.
Okay. So I don't know if I have a question similar to that. I don't remember it. Okay, for example, this, they ask you define electric potential at a point. So this is more clear. So then you go about saying it is the work done per unit charge and bringing it from infinity to a defined point. There are other questions. If you do QPs, you'll see the trend. But yeah, going on. Okay. What was this? Okay, till this we're done. I'm going to cover one more thing. I don't want to touch spherical conductors. So, how to derive electric field strength equation from electric potential equation? We have derived, we have not derived the Coulomb law equation, that is the force equation. It is just a given set of proportionalities between force and charge and separation, and we joined it together to get the force equation. This is the force equation. And from this, we found out EFS. So in case of EFS, it's now basically divided by the test charge. This is the electric field strength. So the force per unit charge. Okay. So how do I find the same electric field strength equation in a different way? That's a question. And it's important because it's in your syllabus. We can actually find electric field strength from a different starting point, and I'll explain how. So one way is to divide the force equation by the test charge, and you get to electric field strength equation, which you guys are okay with and know of. The other is by integrating something, and I'll explain what in a while. So remember that when you have a typical force and a distance curve, right? Force, distance. And what is this region of space that I've shaded going from R1 to R2? So I have Q1 over here, and I take this Q2, which is at R2 and then to R1. So what is this region of space that I've shaded?
Work done.
This work done, right? Perfect. So that is the work done, or electric potential energy, right? Sorry, it goes till infinity. That is R1 to R2 is the work done in taking it from one point to another, change in EPE, change in electric potential energy. So change in electric potential energy is going from R1 to R2. But what I want to highlight is bringing a charge from infinity to a defined point R. Let's say over here, what is the work done? That is the electric potential energy, EPE, right? So when I integrate this region of space under the curve, I get electric potential energy of both Q1 and Q2. Are we clear on that? Why it is of both Q1 and Q2? Yeah, just a bit before I was discussing how the work done, either bringing this charge from infinity or this charge from infinity, will yield the same work done, granted they are isolated in space. So do we get that idea? Yeah, that the electric potential energy is going to be same for Q1 and Q2. Do we get that?
Yes.
Okay. So in this case now, it's the same thing that I'm saying. So if I bring Q2 from infinity to a defined point R, I'm doing a certain amount of work. Okay. And that work is electric potential energy. And you can say it's electric potential energy of Q1 or Q2. Now, the conversation is I have basically integrated the force curve with respect to distance. So when I integrate the force curve, I get work done, electric potential energy. Similarly, if I have the electric field strength curve, E, F, S versus distance, what would I get if I integrate? What do you think you'll get? Yeah, take a guess. I'm integrating electric field strength from infinity to R. So I have a charge over here. So this electric field strength curve defines the electric field strength of Q1. And I'm bringing a test 1 Coulomb of charge from infinity to R1. And this shaded region defines that. So what is this? What is the shaded region? What is the word for it? What energy is this?
Sir, do we need to know how to derive?
Yes, this you need to know. It's not much of a derivation. This one you will need to know. The relationship between both the variables. So what is the shaded region? I'm bringing 1 Coulomb of charge from infinity to R near Q1. How will you define this energy? One Coulomb of charge from infinity to a defined point R near Q1. That is, I've shaded this region, and that is the energy. What would you call this energy? Take a guess. Take a guess.
Electric potential.
Perfect. Electric potential. So this is the electric potential of Q1. So when I integrate electric field strength curve, I get electric potential. When I integrate the force curve, I get electric potential energy. Okay, it's different. It's a different. So one is per unit charge, the other is with any amount of charge. Any amount of charge, that is electric potential energy per unit charge. Okay. So what's the moral right now? When I integrated electric field strength, I got electric potential. So how do I get electric field strength now? What do I do to I don't know which variable over here to get electric field strength? What can I do? How can I get electric field strength from the electric potential? What do I do to electric potential to get electric field strength? Take a guess.
Differentiate.
Perfect. Differentiate. So reverse operation. Yeah. So when I integrate electric field strength, I get electric potential. So the opposite must also be true. If I differentiate electric potential, I should get electric field strength. Let's test this idea. This you need to know. This is why I'm explaining it. This relationship you need to know, which is why I'm showing. It's not much of a derivation, it's just a relationship. Okay. This is the electric potential equation. This is electric potential, right? So what did we establish right now? If I take the derivative of electric potential, I get electric field strength. So let's take the derivative, dV by dr, and on the other side, I'm going to take out the constants. And the derivative of 1 by r will be minus 1 by r squared. Okay, that's the derivative of 1 by r. So now, what do I have? Minus kq1 by r squared. What is this? What do I have? What I have is the negative potential gradient equals the electric field strength. So this minus sign, I took it to the other side. So I multiplied minus on either side. And what I have is minus dV by dr is equals to kq1 by r squared. What is this? Electric field strength. Okay. This is electric field strength. And this is equal to the negative gradient of a potential curve. Want to see that? Let's see. So let's say this is the potential curve of a positive charge. Let's say that. Okay, let's say that. So what happens is, if I want to know, let's say the positive charge is exactly over here, and I want to know what the electric field strength of this positive charge or 5 Coulomb of charge is, 10 meters away. How do I find it from a potential curve? I take the negative gradient at that point. So at this point, I take a slope, right? I find the dV by dr negative of it, and I will get the electric field strength at that point of that charge, 5 Coulomb of charge. So I'll find del V by del R, whatever the value might be, maybe I'll find that, and minus in front of it, I get the electric field strength. That is what you get, the electric field strength. Okay, so you take the gradient on the potential curve at that specific point, and you get electric field strength. Okay, clear? So that is the core idea. And if I want to further explain it, let's go on with a positive charge. Let's analyze a positive charge, and let's analyze a negative charge, right? So let's say with respect to this positive charge, right? I have some amount of charge, I don't know, 5 Coulomb. Notice the field line. The field lines are outwards. Outwards. So let's think about the positive one. What are these circles? This will be called, these are typically in maths, these are called concentric circles. All of these circles have the same center. Okay, that's why it's called concentric circle. It's called a concentric circle. Okay, it's called a concentric circle. Now, the conversation is, what does this concentric circle represent? It's basically what I've drawn is the position where the potential is equal all around. So anywhere on this line that you pick, let's say this is the smallest circle, anywhere on this circle, it will have the same electric potential. So if I bring a test 1 Coulomb of positive charge over here from infinity to this point, what is the energy? Or what is the work done? That is the electric potential. And that work done will be same all around this circle. Got it? Same with electric field strength also. I can also say the same with electric field strength. I can also say that the electric field strength about this circle everywhere is the same. Can I not say that? Yes, I can. Okay. So, but over here, I'm not discussing electric field strength. I'm going to talk about electric potential. So this concentric circle defines 20 volt. Okay. 20 volt. Over here, it defines 15 volt. Okay. Over here, it defines 10 volt. Over here, it defines 5 volt. So everywhere in this circle, 5 volt. Why volt? Why volt? Can anyone tell me? Why volt? Where do I define it? Okay. Yeah, why volt? Any idea? Nope. Nope. Okay. So what is the definition of voltage? Yeah.
Done per unit charge.
Yes. Voltage is work done per unit charge. Okay. So what is electric potential? Work done per unit charge, bringing it from infinity to a defined point. Okay. That is why you see volt over here. Got it? That's why you see volt over here. That is the work done on per unit of charge, bringing it from infinity to that point. That's why you see volt. Okay, that's the idea. So again, coming back, notice what is happening over here. What is the difference between 20 and 15 volt? 5 volt. What is the difference between 15 and 10? 5 volt. Difference between 10 and 5? 5 volt. But notice at the spacing. From 20 to 15 volt, spacing is small. From 15 to 10 volt, spacing is big. From 10 to 5, the spacing is even bigger. Do you need to know this? 100%. They will ask you to draw these circles, potential circles. Okay? The concentric circles represent the potential around the charge. They will ask you this. One of the common questions. They'll ask you to draw a diagram. This is how you draw. So notice that for the same difference in potential, as you move away from the charge, the amount of distance increases. Why? Why? Because of this. As my separation increases, my potential decreases. Okay, it decreases, right? So the amount of
Do we
energy.
need to know why, like theoretically?
Yes, I mean technically yes. They may ask you questions. So like, they may ask you that. Oh, I'm thinking of how to structure the question, but they may ask you why does it take uh, uh, why does it need to why does a test charge need to traverse a longer distance to have the same work done going from 5 to 10 up as opposed to going from 10 to 15 while the amount of work done is same, the distance traversed is different. They may ask you why that's the case. They may, I don't know, might just it's not uncommon nor is it out of your syllabus. Okay,
Yeah.
so why is that?
So sir, this is
Yeah.
around a charge, right?
Yeah, around the charge.
But isn't this as the same as at a point in an electric field?
Sorry, I didn't get you. What?
Like
Isn't
before
this
this,
the
we
same as?
studied electric potential at a point in an electric field, right?
Yeah,
And now we're studying for around a charge.
yeah. So when we were having that discussion, we were just pointing at this specific point and saying what is the electric potential 10 meters away. So now I'm just saying what is the electric potential 10 meters away all around the point. So I've just drawn that circle. Got it?
All right.
Yeah, so you're right. Well, what you're saying that initially we were just saying picking a point and saying it's 10 meters away, what's the electric potential here? And now I'm just doing it all around the circle. You're seeing this in 2D, it is also true in 3D. In that case, you see a sphere. Okay, so it's a sphere over there, and it's bigger sphere as you move away from the point charge. Anyways, what I was saying is, why is it increasing distances? That is because the force doesn't remain constant. So if you look at the force curve over here, so you just need to move a small distance over here to have a certain amount of work done. To have the same work done at a lower force, you need to traverse a greater distance to have the same amount of work done as this. So basically, the force doesn't remain constant. Near the charge, force is greater. So you just need to travel a small distance. Okay. And when you're further away, you need to travel a greater distance. So basically, that's why the amount of distance traversed as you move away increases for the same amount of work done. Okay, so point is force doesn't remain constant, it decreases at a rate of 1 by r square. Okay, so that is why. Now, for the positive charge, again, why is this on the positive axis? Can you tell me? And why is this on the negative axis for the negative charge? Any idea? Energy. Yeah.
Can you say that again?
So why is the electric potential over here for the positive charge on the positive axis? And why is the electric potential for the negative charge over here on the negative axis?
For the positive charge, it's on the
Yeah.
positive because the charge is positive, and on the negative, the charge is negative. So
Okay.
the potential.
Got it.
So the
Okay. Okay. So you're saying it's positive charge, so in the positive axis, it's negative charge, so negative axis. Fair. But you can also explain it by saying what happens when I bring in a test positive charge. Okay. So when you bring in a test positive charge, what happens is the electric potential energy is positive. What happens when you bring in a test positive charge here? The electric potential energy is
Negative.
negative. So remember, towards the beginning of today's class, I said we always think with respect to a test positive charge. The reason I said that towards the beginning of the class is you will come across this again and again and again. Okay, over here, even when you're drawing the diagram, you're seeing one is in the positive axis, one is in the negative axis. Why? Because we're thinking with respect to a test positive charge. If I bring in a test positive charge, this is the standard. This is the standard. Okay, that is why we do it. And it makes sense. It's a negative charge, negative axis, positive charge, positive axis. Also makes sense. It's just that it's nothing right or wrong. It's simply the standard that we choose. It's just a standard to think, just like convention, convention direct current. It goes from positive to negative. It's just a standard that we select, right? It's not inherently right or wrong. It's simply what we consider. So that's why we have on the positive axis and we have on the negative axis. So now when you plot, see, I take the 20 volt concentric circle and I plot it here. It's somewhere over here. Do the same somewhere here. Do the same somewhere here. Do the same somewhere here. So notice we're going from 20 to 15 to 10 to 5. These are the points. Okay. So now I have drawn a voltage curve or potential curve with respect to separation of a test positive charge. Let's say 5 Coulomb. Similarly, negative 5 Coulomb over here. And the field lines, the arrows are, by the way, field lines. Okay. So now, same thing. It's negative 20, negative 15, negative 10, negative 5. And it's in the negative axis because of the reason I just explained. Is there anything else? Yeah, there is. So now you just plot in the points and you have your electric potential for a negative charge. Got it? That's why they are different. Great. Last thing I will say in 5 minutes. What did we learn? What is the electric field strength? Well, how can we represent the electric field strength? We can say it is negative del V by negative del R. Okay. This is what we found out by the relationship of differentiation. When we take the different derivative of the potential curve, we get the electric field strength, negative derivative. Okay, but I'll show it again. This gradient over here is what? Positive or negative? Then
negative.
negative, right? So the gradient over here is negative, but for positive charges interacting, right? Doesn't matter positive or negative charges interacting. The force will be, let's say it is in line with this direction. It can be positive, right? Or let's say it is positive. So you just take the negative gradient of this such that the gradient will be negative, but you have a negative sign in front, and ultimately the answer that you get will be positive. So that denotes the force. Well, I mean, I don't have the setup over here, Like I haven't said which direction is positive or which direction is negative, but you get the idea. Why do I have the negative sign over here? That is what I was trying to flag post. If I had a complete setup, you would see the complete picture. But the reason of this negative sign is so that this negative gradient is or can be changed, right? So this is an inherent property of doing the, you know, uh, differentiation over here. We get the minus sign out of that. And it makes sense because when you see in situations like over here, this is next class, you will see this over here. The negative, when we have set a positive and negative direction, and we take the negative gradient of the potential curve, we get the true direction of the force. We get the true direction of the force. And these curves will be very important to understand. I have covered this a bit more than it is in your syllabus, and most people will teach because I have a feeling they can throw a few curveballs in this topic. So I have done a bit more than you will usually see in the syllabus or in most materials. That is, I'll tell you what is extra. Often this axis is not shown. Then what happens inside, some people cover. Yeah, this axis often people don't really show, but it's important. But when I teach this, I'll explain how the negative gradient of a potential curve is very important. Why the negative is very important, because it truly gives the right direction of the force. Okay, that's why it's important. We cover a lot in spherical conductors. So point being that the negative gradient of a potential curve gives us the electric field strength. Now, you can't just apply this for a spherical conductor, my friend. If you have a spherical conductor like this, and I tell you that there is a potential over here of 10 volt, and further away there is let's say 2 volt. Separation here, let's say, is 10 meters. You cannot apply the formula over here and say 10 minus 2 is 8 divided by whatever is the separation, 10 meters, 10 meters. The answer is not. The electric field strength in this region is not going to be, what is the separation going to be? 4 by 5. Yeah, the answer is not 4 by 5. Okay. The electric field strength in this region is not going to be 4 by 5. Doesn't apply in spherical conductors. Don't make this mistake. Why? Because in case of spherical conductors, the field strength varies as you move away from the charge, whatever velocity. So point is, in case of field strength of positive point charges or spherical conductors, it changes between any separation. It is not constant. It is not constant. Okay, so you can't just apply this. You can't just apply del V by del D. No, doesn't apply. Doesn't work. Doesn't work. You do this with the curve. With the curve you get, the graph that you get. You don't just pluck out the values, find the distance, and call it a thing. No, that's not how it works. If you have the graph and you find the gradient at a certain point, what is the electric field strength at this point? Yes, you can find it out. You take the gradient of that point and you get the electric field strength, negative gradient. You don't just take two values over here on the potential and say, okay, there's a delta of 5 volt divided by whatever the separation is, let's say 10 meters, and this is the electric field strength all across this disk. Nope, that's not how it works. Don't do this. A lot of people have this confusion and do this mistake. Don't do that. That's not the thing to do. This only applies to plates. This equation, del V by del D, only applies to uniform fields. So let's say I have a plate of positive charge, a plate of negative charge, uniformly distributed. The field strength over here, and here, and here, and here, same or different? Quickly, same or different? Electric field strength over there. Same, perfect. So the field strength or force applied on a charge anywhere over here, same. Okay, because uniform fields. So over here, how do you find the electric field strength? Whatever the PD is, del V is over here, they'll give you a voltage potential difference over here. So you take that value, whatever the potential difference is, del V is, divided by whatever the separation is, R, that is the electric field strength, EFS. That is what? The electric field strength in this region. So it applies where? With charged plates. When you have charged plates, there are electric fields in this region, anywhere, the field strength is same. Okay, that's where this del V by del T works. And this is one of the more common thing. Setup, you will see, you'll learn about capacitors. You'll see how it applies. Okay, this is the separation, you'll see a del V. Okay, you'll see a del V. Okay, so I've explained all of this, why it doesn't work for point charges, because it changes, the electric field strength changes with distance with a 1 by r squared relationship. Last thing, spherical conductors, which is pretty darn long. And motion of charged particles, that is pretty much nothing. Last thing is spherical conductors. Yeah. So we're done with everything. Any question till now? Any other question? All good? Okay. Everything okay? Okay, perfect. So we're done for today. If you have any question, you're welcome to ask. And we're gonna have a class tomorrow, same time. That is 3 p.m. PST. Okay. British summertime. Today I have to delay a bit, sorry, but tomorrow it's gonna be the same time. Okay. Okay. So I'll end the class then for today. Thank you guys. See you guys tomorrow. Okay.